Hello everyone. We are starting a free open lecture right now in our Discord. All our lectures are held weekly without breaks. If you, the viewer, want to ask questions and get answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. To find out the schedule of the lectures, please kindly join our Telegram channel and stay updated. Here we also have the third, an important request coming in. We are currently doing something over there, at that particular place, somewhere perhaps. Please make a request from our comprehensive offer. And here is the third request, now waiting for a response. They are waiting. The time comes for this one, and indeed the first. And certainly, our first task has indeed received a response. Accordingly, as soon as it received the response, our processor is already busy doing something, processing that response. So here our processor is loaded. Well, conditionally speaking, it returned that response to the user, or did something with it, and now the time for the response of such a task is approaching. Accordingly, the processor is already handling the second task, processing the response, and sending it. It is free again, and here comes the response from the third task. It is also processed and sent to the user. And if we look at the time it took to execute these requests, we have here approximately 1/100th of a second, then here about 1 second, and here 1/100th of a second. Accordingly, the first request was processed in approximately around 102 seconds. How long did the second request approximately require to process from the very beginning? PFSP. So here it is, 1.02 seconds, and here another 0.01, in total 1.03 seconds. It is essential to note that the third request took a total of 1.04 seconds. Accordingly, as a result of this, if we just simply look at the time difference carefully and precisely in a detailed manner from here to each and every one of the ends, so overall, we have already established that each of these requests was processed on average in 1 second. This allowed us to use resources effectively during the wait. And this is essentially, in a nutshell, to put it simply, roughly how our asynchronous processing works.
Want to become a great programmer? Subscribe to our Telegram channel.
Accordingly, how to optimize our application. I definitely submit the Russian one if we are indeed certainly going to use the asynchronous pattern. Firstly, we will certainly have to definitely ensure that we make all operations related to waiting asynchronous, because if we do not make some operation asynchronous, which is related with waiting, performance can drop significantly because synchrony is, as it is, primarily designed for I/O-bound loads. It handles them well. To fix our application here, we were sending a request, usually requests, in Python, refer to the requests library. But here, we will have to use another library that supports asynchronicity. This is either UHTTP or HTTPX, which can specifically be used in both directions, without asynchronicity and asynchronously. For it to work with asynchronicity, we essentially need async click. Well, here, in the application code, instead of sending a request, that's what I did. First of all, send request also became asynchronous. And where there used to be just time sleep, I made a synchronous sleep, which you could say works exactly the same as in runaway. This synchronous sleep is designed to enhance functionality by providing a more efficient alternative to time sleep. There will also be waiting here. And this waiting will allow a bit of transitioning to execution. We'll look at how this works in more detail in the process later. And now, if we run this particular application, which is designed to handle multiple tasks simultaneously and send several requests in parallel, we can clearly observe that each individual request was processed efficiently in about 1 second. There were 1, 2, 3, 4, 5, here all approximately 1. The second option is concurrency. So, if we use the synchronous approach here, then we will need to use threads here. In this context, it is crucial to understand that multiple threads are necessary, and threads are quite a basic thing in programming. They allow inputs to go directly into the operating network. Music in general. Will be able. Music in general. Music plays in the video. We can communicate. All this will happen without any delay on our computer. We understand that everything works simultaneously in parallel. But in reality, it's not quite like that. And how will this work? Each request processing function will run in a separate thread. And this thread will make it pseudo-parallel, in a sense. Accordingly, if several requests come in, these requests will be processed in a way that is parallel, in a timely manner. Let's carefully and closely look at pictures to observe how this will actually happen. Here, if we simply take a couple of threads, we can just take more, but for instance, let's take 2. How can they be executed? They can either be executed in parallel on different cores of the process, or they can be executed concurrently on one core. In that case, their execution will alternate. Well, the order of execution of all threads in computers is regulated by the operating system scheduler. But what does it mean that this execution will alternate? If parallel execution is relatively clear, they started at one moment in time, and like this they... And what does it mean to execute concurrently? Here we have 2 tasks, red and green. Here it is processed a little at the beginning, then there is a blue wait, and at the end it processes a little more. When it's blue, the processor is not busy, and the green task is exactly the same, meaning it processes a little at the beginning, then waits, and at the end processes a little more. If we execute these tasks sequentially, it is also called synchronously. This is how it was in our application at the very beginning. That's how it works. If they arrive at the same moment in time, the first one is executed first. Then, as soon as it finishes, the second one is executed. If there is 1 second everywhere, then, accordingly, the first task is completed in 1 second, while the second takes 2. What does concurrency allow? It will switch back and forth between these tasks. That is, it will perform several operations from the first task, then switch to the second task, and also perform several operations from it. Then it will return to the first task, continue its execution again, but just a little. It will return to the second task.
TFSP.
It will also continue to carry out it for some time. Then, for example, we have waiting here and here. Red, green, red, green. It switched a little. This is the scheduler for these threads. Then we have waiting, respectively, blue and brown. And since the processor is not used during waiting, what is happening here in this particular scenario? We switch to this task and we see it is sleeping. Accordingly, if it is sleeping, we can switch to another task. She is also sleeping, so he starts to step between them, but this is under ideal conditions where no processes are running on the computer. Well, of course, as expected, there will always be something. There will be a lot of switching. But if we take such a specific environment, then here, in this particular scenario, he will indeed alternate between them, and it will turn out that the first task and the second task will not switch until a total of 1 second passes, because, for example, this blue bar is at the specific mark of, say, approximately 0.2 seconds. Then, when the first task is supposed to successfully receive a response, it should get the answer 1 second from here, which means a total time of 1.02 seconds, as anticipated. And the second task, since it sent a request somewhere at the same moment, should also receive a response at that moment in time, 1.02 seconds. And it turns out that both tasks are sleeping, meaning the processor is idle for only 1 second. And then this switching starts again, right? You know, they switch, but they both waited a total of 1 second. And it turns out to be exactly the same situation as ours. On average, the request time is 1 second because all our tasks wait in parallel, not sequentially. What were they waiting for in parallel here? What are they waiting for in parallel here?
TFSP.
The application code is actually very simple. We just need to remove the async function from here, as the Ethernet web server is already oriented for us. If an asynchronous function tries to handle its load through asynchronicity, well, if we break it further, that's also a fault. And if the function is a regular, non-asynchronous one, it essentially uses a concurrent approach here to enhance the efficiency of the application, and runs this processing function in a separate thread, which can then be established further. And in such a situation, typically, each request should ideally be processed in approximately about a second, generally speaking.
Want to become a great programmer? Subscribe to our Telegram channel.